Well, we really unpack them to pull out the most important insights.
That's the plan.
And today, we're diving into something that might genuinely reshape how you perceive reality itself. It's called quantization.
Mm-hmm.
At its heart, it's this really radical idea that the universe isn't smooth, continuous. But it's actually built from discrete, indivisible packets.
Like tiny fundamental building blocks.
Exactly. Think of Lego bricks, but for energy, momentum, all that stuff.
Right.
And this isn't just some abstract physics thing floating out there. It's literally the foundation of modern technology. It explains why atoms don't just collapse instantly.
Which would be bad.
Very bad. And even how your smartphone works.
It's truly fundamental, and we're going to trace, the whole intellectual journey of this idea. We'll start with how classical physics, which seemed so perfect, just hit a wall.
Yeah.
Ran into these puzzles that led eventually to the huge insights of quantum mechanics. And what's really remarkable, I think, is how a seemingly small mathematical fix,
like a little tweak.
Yeah, just a tweak, turned into this absolute cornerstone of how we understand the universe.
So let's do it. Let's get into this deep dive on quantization. We'll look at its surprising origins, the maths behind it, how it actually shows up in nature.
And the amazing tech it's given us.
Definitely. We're talking a journey from something called the ultraviolet catastrophe all the way to MRIs and maybe even the fabric of space-time itself.
Potentially, yes. It goes deep. The unexpected birth of a radical idea. When classical physics broke down.
Okay, so our journey into quantization kicks off where? Late 19th century.
That's right, end of the 1800s.
And you have to imagine, back then, classical physics, Newton, Maxwell, all those giants, it felt like they'd figured everything out.
It really did. Planetary motion, electricity, magnetism, the framework seemed complete, rock solid.
But then these weird experimental results started popping up, especially when looking at really small stuff, the atomic scale things.
Puzzles that classical physics just had no answer for. It completely broke down.
So what was the killer problem? What was the thing that showed classical physics just wasn't the whole story?
Well, the first big crack appeared with something called black body radiation. It sounds technical, but think of an idealized object, something that perfectly absorbs and then emits all frequencies of light when it gets hot.
Like a perfect theoretical oven, maybe. You heat it up, it glows.
Exactly, a perfect absorber, perfect emitter. Physicists tried to use classical physics to predict the spectrum of light, the colors and intensities that this ideal object would emit at different temperatures.
Okay, makes sense. What did classical theory predict?
It predicted something completely absurd. The Rayleigh-Jeans law, based on classical ideas, said that these black bodies should emit an infinite amount of energy.
Infinite.
Infinite. Especially at the short wavelengths, ultraviolet light and beyond. This was famously called the ultraviolet catastrophe.
Catastrophe sounds about right for infinite energy.
It wasn't just a small mismatch with experiments, it was a violent, fundamental contradiction. If that law were right, even a warm teacup should be blasting out deadly levels of UV radiation. Clearly, something was deeply wrong.
Okay, so classical physics hits a brick wall. Enter Max Planck. You called him a reluctant revolutionary.
Very reluctant. He was deeply rooted in classical physics, thermodynamics. He wasn't looking to overturn anything. He even called his own solution an act of desperation.
Desperation. Why? What did he do?
Well, in December 1900, to force his calculations to match the actual experimental data for black body radiation, Planck had to make this incredibly radical assumption.
Which was?
He proposed that the little vibrating oscillators inside the walls of the black body couldn't just absorb or emit any amount of energy. They could only do it in discrete chunks, little packets.
Some packets.
We called them quanta. And the energy E of each quantum was directly proportional to its frequency, F, linked by this tiny, tiny number we now call Planck's constant, H. So E equals HF.
EHF. So energy isn't like a smooth ramp you can slide up and down.
Yeah.
It's like a staircase. You can only be on step 1 or step 2 or step 3. Nothing in between.
Precisely. Specific allowed energy levels. But the key thing is, Planck himself really didn't like this idea.
He didn't believe his own solution.
Not really, no. He saw it as a mathematical trick, a fudge factor, just something he needed to make the math work out. He spent years trying to derive his radiation law without resorting to quanta. He hoped it was just, a computational shortcut.
Huh. So the revolution wasn't his intention, but the implication.
The implication was unavoidable, that energy itself, at some fundamental level, might be grainy. 2. The photon. Einstein solidifies the quantum.
Okay, so Planck kind of cracks the door open, maybe accidentally,
Reluctantly, yes.
but then along comes Albert Einstein, who just kicks the door down.
You could say that. In 1905, his famous miracle year, he wasn't looking at black bodies. He tackled a different puzzle entirely, the photoelectric effect.
Right, the photoelectric effect.
Yeah.
That's when light hits metal and electrons pop out.
Exactly. And classical physics, thinking of light purely as a wave, couldn't explain several key experimental facts about this effect.
Like what? What didn't make sense?
Well, for one, classical wave theory predicted that if you shone brighter light, a more intense wave, the electrons knocked out should have more energy, more kinetic energy.
Okay, that seems logical. More wave energy pushes them harder.
Seems logical, but it's not what happened. Experiments showed the maximum energy of the ejected electrons depended only on the light's frequency, its color, not its brightness at all.
So blue light knocked out higher energy electrons than red light, even if the red light was much brighter.
Precisely. Brighter light just knocked out more electrons, but their individual maximum energy didn't change. That was puzzle number one.
What else?
Classical theory also predicted a time delay. If the light was very dim, it should take time for the wave to transfer enough energy to an electron to kick it out.
Like slowly filling a bucket until it overflows.
Kind of, but experiments showed the emission was instantaneous. As soon as the light hit, electrons came out, even with incredibly faint light. No delay.
And wasn't there something about a minimum frequency?
Yes, the threshold frequency. Below a certain frequency, a certain color, no electrons were ejected at all, no matter how intense, how bright you made that light. Classical waves just couldn't explain that cutoff.
So classical waves fail again. What was Einstein's insight?
Einstein took Planck's quanta idea and ran with it. He proposed something truly revolutionary, that quantization wasn't just about how matter emits or absorbs energy, but that light itself is inherently quantized.
Light itself is packets.
Yes. He said light consists of discrete, particle-like packets of energy. He called them light quanta. Initially, we now call them photons. And crucially, the energy of each photon was given by Planck's same formula, E en pith.
So he basically looked at Planck's mathematical trick and said, nope, this is real. This is what light is.
Exactly that. He declared it a physical reality. In his model, the photoelectric effect becomes a simple one-to-one collision.
One photon hits one electron.
Right. If that single photon's energy, HF, is greater than the minimum energy the electron needs to escape the material that's called the work function,
Okay.
then the electron is instantly knocked out. Any leftover energy from the photon becomes the electron's kinetic energy. So kinetic energy equals HF minus the work function.
And that perfectly explained everything.
Perfectly. The electron's energy depends on the photon's frequency, color, not the number of photons, brightness. There's no time lag because it's an instant collision. And the threshold frequency exists because if a single photon doesn't have enough energy, HF is too small, it can't knock out an electron no matter how many photons you send.
That's incredibly elegant. But you said he called it heuristic at first, like a useful idea, but maybe not the final truth.
He did present it somewhat cautiously as a heuristic viewpoint, but its sheer success in explaining every detail of the photoelectric effect was undeniable. That work eventually won him the Nobel Prize in 1921.
But what really sealed the deal, what made everyone accept the photon as real?
The truly decisive evidence came a bit later, in 1923, from Arthur Compton's experiments. He scattered X-rays off electrons.
High-energy photons.
Exactly. And he found that the X-rays scattered exactly as if they were tiny particles, like little billiard balls colliding with the electrons, carrying not just energy, but also definite momentum.
So they bounced off like particles.
Precisely. The results matched the particle collision calculations perfectly. After Compton's work, the physical reality of the photon was basically undeniable. Light really was both a wave and a particle. 3. The mathematical heartbeat of a quantized world.
Okay, so Planck stumbles upon quantization. Einstein embraces it for light. But this still feels a bit like discovering phenomena. What's the deeper reason? Why is the universe built this way? Where does the math come in?
Now we get to the heart of it. This leads us straight into the development of modern quantum mechanics in the mid-1920s. Think Heisenberg, Schrödinger, Born, Dirac. These brilliant minds built a completely new mathematical framework.
A new rule book for reality.
Essentially, yes. And in this framework, quantization isn't something you put in by hand. It emerges naturally, inevitably, from the mathematics itself.
Okay, let's try to unpack that. How does this new math describe, say, an electron? No more little planets orbiting.
No more classical orbits. Instead, the state of a quantum system, like an electron, is described by a mathematical entity called the wave function, usually written as psi, the Greek letter eh.
A wave function. Is it a wave in physical space?
Not exactly, it's more abstract. Think of it as a wave of probability. Its value at any point tells you something about the likelihood of finding the particle there. Specifically, if you take the square of its magnitude, that gives you the probability density.
Probability. Okay, so it doesn't tell you where the electron is, but where it might be.
Precisely. And these wave functions don't live in our normal 3D space. They exist in a much larger, more abstract mathematical space called a Hilbert space. It's a complex space that holds all possible states the system could be in.
Hilbert space. Right. And how do we get actual measurable things like energy or momentum out of this wave function?
This is where operators come in. In quantum mechanics, every physical quantity you can measure, energy, momentum, position, angular momentum, what they call an observable, corresponds to a specific mathematical operation, an operator.
Like a mathematical recipe.
Kind of, yeah. An instruction that acts on the wave function. For example, the momentum operator involves taking a derivative, a specific kind of mathematical change. And these operators have a special property called being Hermitian, which basically just guarantees that the results of measurements will always be real numbers, not imaginary ones.
Okay, wave functions, operators. But where's the quantization? Where do the discrete steps come from?
It comes from something called the eigenvalue equation. This is really central. Sometimes when an operator acts on a very specific kind of wave function called an eigenfunction, the result isn't some complicated new function. It's just the original wave function back again, multiplied by a simple number.
The operator spits the function back out, just scaled by a number?
Exactly. And that number is called the eigenvalue. Now, here's the fundamental rule. The only possible results you can ever get when you measure that physical quantity are these specific eigenvalues. Nothing else.
Ah, so the eigenvalues are the allowed quantized values.
Precisely. The set of eigenvalues for the energy operator, for example, gives you the allowed energy levels of the system.
Okay, but why only those specific wave functions and eigenvalues? Why not others?
This is where the idea of bound systems becomes crucial. Think about something simple, like a guitar string tied down at both ends.
Okay.
When you pluck it, it can't just vibrate any old way, can it? It can only sustain vibrations at specific frequencies, the ones where a whole number of half wavelengths fit perfectly along the string. Those are its resonant modes, its standing waves.
Right, you get distinct notes.
Exactly. It's the same idea for an electron bound inside an atom. The electron's wave function is confined by the atom's electric field, like the guitar string is confined by its fixed ends. The wave function has to fit within that boundary.
It has to satisfy boundary conditions.
Yes. And only certain wave function shapes, certain standing wave patterns, satisfy those conditions. These specific allowed wave patterns are the eigenfunctions, and their corresponding energies are the discrete, quantized eigenvalues, the allowed energy levels.
The guitar string analogy really helps. So
Yeah.
quantization naturally arises from the wave nature of particles being confined.
That's a great way to put it for bound systems, yes.
What about measurement then? If a system can be in multiple states, how does measurement work? Is it still deterministic?
Not in the quantum world. A general quantum state is often a superposition, a combination, a mix of many different possible eigenstates. It's like the guitar string vibrating with several of its allowed notes simultaneously.
Okay.
When you perform a measurement, say, you measure the energy, the outcome is fundamentally probabilistic. You don't know beforehand which result you'll get. You'll always get one of the allowed eigenvalues, but which one is random
And the probability of getting each result.
is determined by the wave function itself, specifically by how much of each eigenstate is in the superposition. This is calculated using the Born rule. And here's the really weird part. The act of measurement itself forces the system to choose. It collapses the wave function, snapping it out of the superposition and into the single eigenstate corresponding to the value you just measured.
Measurement changes the system. Wow, okay, one more piece. The Heisenberg uncertainty principle. How does that fit into this mathematical picture?
It comes directly from the operators. Remember how each measurable quantity has an operator? Well, it turns out that for certain pairs of quantities, like position and momentum, or energy and time, their corresponding operators do not commute.
Don't commute, meaning the order matters.
Exactly. Applying the position operator, then the momentum operator, gives a different result than applying the momentum operator, then the position operator. Mathematically, their commutator isn't zero. It's related to Planck's constant.
I see. I remember seeing that.
That's the one. This mathematical non-commutativity is the fundamental reason behind the uncertainty principle. It mathematically proves that you cannot simultaneously know the values of both position and momentum with perfect accuracy. It's not a flaw in our measurement devices. It's baked into the very structure of quantum mechanics. It's a defining feature of the quantum world.
Hmm.
4. A taxonomy of quantized values. What gets quantized and how?
So quantization isn't just one thing. It pops up differently for different physical properties, right?
Absolutely. It's useful to look at how it manifests for, say, energy versus angular momentum versus electric charge. They're not all quantized for the same reason.
Let's start with energy. We've touched on this. Bound systems,
Yeah.
like atoms.
Right. The quantization of energy levels in atoms is probably the most famous example. Niels Bohr's early model of the hydrogen atom in 1913 was a crucial step. He just postulated that electrons could only exist in specific orbits with fixed quantized energies.
He didn't fully explain why, but his model worked amazingly well for hydrogen spectrum, didn't it? He derived that formula, NS Rydberg on S.
He did, and it was a breakthrough. But as we said, it still clung to the idea of classical orbits. The modern quantum picture is different.
No orbits, just probability clouds, orbitals.
Exactly. And the discrete energy levels aren't postulates anymore. They are the natural mathematical solutions, the eigenvalues that emerge when you solve the Schrödinger equation for an electron confined within the atom's potential well. It's a direct result of its wave nature being restricted.
Okay, so energy quantization comes from confinement. What about angular momentum? Is that similar?
It has similarities. The magnitude of an electron's orbital angular momentum, think loosely about its motion around the nucleus, is also quantized. It's determined by a quantum number, L.
Right.
But there's something even stranger called space quantization. It means that the direction or orientation of this angular momentum vector in space is also quantized. If you put the atom in a magnetic field, the angular momentum vector can only point in a few specific discrete directions relative to the field, not just anywhere.
It snaps into place, kind of.
Sort of, yes. But then there's spin. This is a whole different beast.
Spin. This came from that Stern-Gerlach experiment.
Yes, in 1922, they shot silver atoms through a non-uniform magnetic field and expected to see a continuous smear on their detector screen based on classical ideas about magnetic moments.
But they didn't get a smear.
No, they got two distinct spots, two discrete groups. This revealed a completely new intrinsic quantum property of the electron, which was later called spin.
And it's not literally spinning like a top.
No, that's just a misleading name, really. It's an intrinsic angular momentum. It's just part of what an electron is, like its charge or its mass. It has no classical counterpart. And for an electron, it's always quantized into one of two values: spin up or spin down. That's it.
So energy and orbital angular momentum quantization arise from the wave mechanics of confined systems.
Correct.
But spin is just fundamentally intrinsically quantum, a built-in two-level system.
Exactly. It's deeper, in a way.
Okay, last one, electric charge. How does that fit in? Is it quantized for similar reasons?
Charge quantization seems different again. Unlike energy or angular momentum, which become quantized due to dynamics and confinement, the quantization of electric charge looks more like a fundamental built-in rule of nature, almost axiomatic.
What's the rule?
All freely existing particles that we've ever observed carry an electric charge that is an exact integer, multiple, 0, 1, import 2, etc., of a fundamental unit, the elementary charge, E, the charge of one electron, or proton.
And Millikan's oil drop experiment proved this right, back in 1909.
Yes, Robert Millikan's meticulous experiments showed conclusively that the charge on tiny oil droplets was always a whole number multiple of this fundamental charge, E. Never, say, 1.5 times E or 0.7 times E.
Always integer steps. But wait, what about quarks? Don't they have fractional charges?
Good point. Yes, quarks, the building blocks inside protons and neutrons, do carry fractional charges, like plus 23e or negative 13e. That seems to break the rule.
So why don't we see fractional charges flying around?
Because of something called color confinement, a feature of the strong nuclear force. Quarks are permanently bound together inside particles like protons, 2 up quarks, 1 down quark, plus 23 plus 23 13 equals plus 1e, and neutrons, 1 up, 2 down, plus 23 13 13 equals 0e. You can never, ever pull a single quark out on its own.
They're always confined in groups that have an intertotal charge.
Precisely. So the rule holds for all free, observable particles. It's a fascinating interplay.
So looking back at this taxonomy, Charge seems like a fundamental rule we observe. Energy and orbital angular momentum are consequences of wave mechanics and confinement. And spin is just inherently quantum.
That's a good summary. It shows quantization isn't monolithic. It arises in different ways at different levels of physics. The profound consequences of a discrete universe.
Okay, we've explored where quantization comes from and how it shows up. But why should you, listening right now, really care about this? What are the big consequences?
Well, the consequences are absolutely enormous. Fundamentally, quantization is why matter itself is stable, why things exist at all.
How so? What's the classical problem?
In classical physics, an electron orbiting a nucleus is an accelerating charge. Accelerating charges should continuously radiate energy electromagnetic waves.
Like a tiny radio antenna.
Exactly. And as it radiates energy away, it should lose energy, spiral inwards, and crash into the nucleus in a fraction of a second.
So classically, atoms should collapse almost instantly.
Yes. If classical physics were the whole story, stable matter as we know it simply couldn't exist. The universe would be a soup of collapsed particles.
Okay, that's a pretty big consequence. How does quantization prevent this atomic apocalypse?
It provides the ultimate fix. Because electron energy levels in an atom are quantized, there's a lowest possible energy state, the ground state.
The bottom step on the staircase.
Right. An electron in the ground state literally cannot lose any more energy by radiating because there are no lower energy levels available for it to transition into. That quantized energy floor prevents the collapse. It guarantees atomic stability.
That's incredible. Quantization is literally why stuff holds together.
Fundamentally, yes. And that same principle, electrons jumping between discrete energy levels, explains another key feature of the universe: atomic spectra.
Those unique fingerprints of light that elements emit or absorb.
Exactly. When an atom absorbs energy, say from heat or light, an electron jumps up to a higher energy level, an excited state.
Okay.
It doesn't stay there long. It wants to fall back down to a lower level. When it does, it releases the energy difference between the two levels as a single photon.
And since the energy levels are discrete, fixed values.
The energy difference between any two levels is also a specific fixed value, which means the emitted photon has a specific energy and therefore a specific frequency, E8 of F. So atoms only emit light at very particular colors, creating those characteristic sharp lines in their spectrum.
And that's how astronomers can tell what distant stars are made of, by reading those spectral lines.
Precisely. Spectroscopy, built entirely on quantized energy levels, is one of our most powerful tools for understanding the cosmos.
What other big ideas flow directly from quantization in quantum mechanics?
Well, as we discussed, the Heisenberg uncertainty principle is a direct mathematical consequence of the non-commuting operators inherent in the quantized framework. It's not about measurement limitations. It's fundamental.
You can't know everything perfectly.
Not certain pairs of things like position and momentum, no. Then there's wave-particle duality. Quantum mechanics naturally incorporates the idea that things like electrons and photons can behave as both waves and particles, depending on the experiment.
The context matters.
Yes. And maybe the strangest consequence for multiple particles is entanglement.
Ah, entanglement. Einstein's spooky action at a distance.
That's the one. Particles can become linked in such a way that they share a single quantum state no matter how far apart they are. If you measure a property of one particle, you instantly know the corresponding property of the other faster than light could travel between them.
Which seems impossible, but experiments confirm it.
They do. It's a direct consequence of how quantum states are described mathematically, their non-local nature. It all stems from this underlying quantized structure of reality.
It really is amazing how these core ideas, quantization, superposition, uncertainty, entanglement, are all just different facets of the same underlying and very weird quantum reality. 6. Quantization in action, building our modern world. So it stabilizes atoms, explains spectra, leads to uncertainty and entanglement. But quantization isn't just theoretical, it's incredibly practical, right? It's the engine behind a lot of modern technology.
Oh, absolutely. Our modern world would be unrecognizable without technologies based directly on quantum principles, primarily quantization. Let's take lasers, for example.
Laser. Light amplification by stimulated emission of radiation. That sounds quantum.
It absolutely is. The stimulated emission part was first predicted by Einstein based on quantized energy levels.
How does it work? How do you get that intense, focused beam?
Okay, so imagine you have atoms with specific quantized energy levels. If an electron is in a higher energy state, an excited state, a passing photon with exactly the right energy, the energy difference between that state and a lower one can trigger the electron to drop down.
Stimulated to drop.
Yes, and when it drops, it emits a second photon that is absolutely identical to the first one, same energy, same direction, same phase. They're perfectly coherent.
So one photon becomes two identical photons. That's the amplification part.
That's the start of it. To get significant amplification, you need more atoms in the excited state than in the lower state. That's called a population inversion.
How do you achieve that? Normally, more atoms are in lower states.
You have to actively pump energy into the material using light or electricity to push electrons up into that higher excited state. Once you have that inversion, one photon can trigger a cascade, an avalanche of identical photons, bounce them between mirrors, and you get an intense, coherent laser beam.
And the specific energy levels of the atoms determine the color and power of the laser.
Exactly. Engineers carefully choose materials with specific quantized energy level structures. 3-level systems, 4-level systems to create different types of lasers, from tiny laser pointers to powerful industrial cutters. It's quantum engineering.
Okay, lasers rely on discrete energy levels. What about semiconductors? The heart of all computers and electronics.
Semiconductors are perhaps the most widespread application of quantum mechanics. Their behavior is completely inexplicable classically.
Why? What's the quantum explanation?
In a solid crystal, the huge number of interacting atoms causes the discrete energy levels of individual atoms to spread out and merge into continuous bands of allowed energy.
Energy bands instead of sharp levels.
Right. There's typically a lower band filled with electrons, called the valence band, and a higher, mostly empty band called the conduction band. Crucially, there's often an energy gap between them, the band gap.
And that gap determines if it's a conductor, insulator, or semiconductor.
Precisely. Conductors have overlapping bands or no gap, insulators have a huge gap, and semiconductors have a small, manageable gap. The magic comes when we control that gap and the electrons near it.
How do we do that?
Through doping. We deliberately introduce tiny amounts of specific impurity atoms into the semiconductor crystal.
Like adding a pinch of salt.
A very precise pinch. If you add atoms with extra valence electrons, like phosphorus and silicon, you create an N-type semiconductor with extra electrons available for conduction near the conduction band. If you add atoms with fewer valence electrons, like boron, you create holes missing electrons in the valence band, making a P-type semiconductor.
And you're essentially adding specific quantized energy levels within the band gap.
You are. Doping allows incredibly precise control over the material's conductivity. And when you put N-type and P-type materials together, you create a PN junction.
The fundamental building block of transistors and diodes.
Exactly. The entire digital revolution runs on our ability to engineer these quantum energy bands and control electron flow across PN junctions. Even phenomena like quantum tunneling, where electrons can pass through thin insulating barriers they classically shouldn't be able to cross, are essential for things like flash memory and USB drives and SSDs.
So no quantum mechanics, no computers as we know them. Wow. Okay, one more. MRI scans. Medical imaging. How is that quantum?
MRI magnetic resonance imaging is a fantastic application of the quantization of nuclear spin. It mostly looks at the spin of hydrogen nuclei, which are just single protons, and are super abundant in the water and fat in our bodies.
Protons have spin, like electrons.
They do. They're also spin 12 particles. This means their intrinsic spin angular momentum is quantized. When you put them in a strong magnetic field, like inside an MRI scanner, their spins can only align in two possible orientations relative to the field: spin up, parallel lower energy, or spin down, anti-parallel higher energy.
Only two options. Quantized again.
Quantized again. In the strong magnet, slightly more protons will naturally settle into the lower energy spin-up state.
Okay, so how do you get an image from that?
You then hit the body with a pulse of radio waves, RF energy. But not just any radio waves, they have to be tuned to exactly the energy difference between the spin-up and spin-down states. This is the resonance condition.
Like tuning a radio to the right station.
Precisely. This RF pulse provides the energy needed to flip some of the spin-up protons into the higher energy spin-down state.
So you excite them.
You excite them. Then you turn the RF pulse off. The excited protons will naturally relax back down to the lower energy state, and as they do, they emit their own faint radio signal. The MRI machine detects these signals.
And different tissues emit different signals.
That's the key. Protons in different types of tissue, like fat, muscle, brain matter, water, relax back at different rates. These are called the T1 and T2 relaxation times. By carefully designing the sequence of RF pulses and listening to the timing and strength of the returning signals, the MRI scanner can distinguish between different tissues.
And build up a picture slice by slice.
Yes. To get spatial information to know where the signals are coming from, they use weaker, varying magnetic fields called gradients. These gradients make the resonance frequencies slightly different at different locations in the body. By analyzing the frequencies of the returning signals, the computer can reconstruct a detailed 3D image of soft tissues, which is incredibly valuable for medical diagnosis. It's all based on manipulating and measuring quantized nuclear spins. 7. The ultimate frontier. Quantizing fields and spacetime itself?
We've gone from atoms to lasers to MRI. Quantization is clearly everywhere in matter and technology, but what about the truly fundamental level? What about the fields that permeate the universe? What about space-time itself? Is that quantized too?
Now you're asking the really big questions, pushing towards the frontiers of theoretical physics. The framework that describes fundamental particles and forces everything except gravity, that is quantum field theory, or QFT.
QFT, how does that relate to quantization?
QFT takes quantization to a whole new level. Instead of just quantizing properties of particles like energy or spin, QFT quantizes the underlying fields themselves.
Wait, so particles aren't the most fundamental thing, fields are.
In the QFT picture, yes, fields are the fundamental reality filling all of space and time. Things we perceive as particles, electrons, photons, quarks are understood as localized quantized excitations or vibrations of their corresponding fields.
Like ripples on a pond.
Exactly like ripples on a pond, or maybe knots of energy in the field. A photon is a quantum of excitation in the electromagnetic field. An electron is a quantum of excitation in the electron field. This view naturally explains how particles can be created and destroyed. You're just adding or removing energy ripples from the field.
Okay, so QFT successfully quantizes the fields for electromagnetism and the nuclear forces. But Isaac said gravity, that's the elephant in the room, isn't it?
It's the biggest elephant in physics, yes. The grand challenge is unifying quantum mechanics, specifically QFT, with Einstein's theory of general relativity, which describes gravity.
And general relativity describes gravity as the curvature of space-time, which is smooth and continuous, right?
Exactly. That's the core conflict. QFT describes a reality built on discrete quanta and probabilistic fields, while general relativity describes gravity as the geometry of a smooth, continuous space-time continuum. They're built on fundamentally different, seemingly contradictory assumptions.
What happens if you just try to apply the QFT recipe to gravity? Try to quantize the gravitational field?
People have tried for decades. The most straightforward approach is to postulate a particle for gravity, the graviton, which would be a quantum of the gravitational field. But when you try to calculate interactions involving gravitons using standard QFT techniques, the math goes haywire. You get uncontrollable infinities that you can't easily get rid of. The standard methods just break down.
So simply quantizing the gravitational field like the others doesn't seem to work. Does that mean space-time itself needs to be quantized?
That's the logical direction many physicists are exploring. The argument goes, matter and energy are quantized, described by QFT. Matter and energy are the source of gravity, which is the curvature of space-time, according to general relativity. Therefore, if the source is quantum, the space-time geometry it creates must ultimately be subject to quantum rules too.
So the smooth picture of space-time is just an approximation.
That's the idea. Just like the smooth surface of water is an approximation of underlying discrete molecules.
So this leads to some pretty wild concepts, doesn't it?
Yeah.
Like space-time foam.
It does. At the incredibly tiny Planck scale, about 10 nanometers, way smaller than anything we can probe directly, many theories predict that space-time itself stops being smooth. It dissolves into a constantly fluctuating, chaotic quantum foam. Yeah, where concepts like definite distance or even the clear order of before and after might lose their meaning. Space-time might become fundamentally uncertain and dynamic at that level.
And perhaps the most radical idea, space-time isn't fundamental at all, but emergent. It arises from something deeper.
That's probably the most profound shift in thinking being explored. Some approaches, like loop quantum gravity, suggest that spacetime itself has a discrete atomic structure at the Planck scale.
Atoms of spacetime.
In a sense, they find that operators corresponding to geometric quantities like area and volume also have discrete eigenvalues, meaning area and volume themselves might be quantized, coming in minimum possible chunks. There might even be a minimum tick of time.
So the smooth, continuous spacetime we experience
Would be an emergent property, A large-scale approximation, like the properties of fluid dynamics emerging from the statistical behavior of countless individual molecules. The truly fundamental reality might not be in space or time at all, but might consist of more abstract things like relationships, networks, or quantum information from which spacetime itself somehow crystallizes.
That's genuinely mind-bending. The idea that space and time aren't the stage, but part of the play itself.
Yeah.
Wow. Okay, so we've covered a huge amount of ground. From Max Planck being unhappy with his own idea.
His act of desperation.
Right. All the way to potentially space-time itself being made of tiny, discrete bits. So let's try to wrap this up. What's the big takeaway for someone listening? Quantization. It's not just one weird quantum rule, is it?
No, not at all. You could argue it's the central defining characteristic of the quantum world. It seems to be woven into reality at every level we've managed to probe.
And we see this pattern, right? The deeper we look, the more things seem to be discrete, not continuous.
That does seem to be the pattern. From those sharp spectral lines that told us atoms had levels, to the energy packets of light, to the very stability of matter. These are all consequences, ultimately, of the wave-like nature of things being confined or interacting in specific ways.
And it has this dual legacy. On one hand, it's the source of all the quantum weirdness.
Yeah.
The uncertainty, the probabilities, entanglement stuff that really messes with our classical intuition.
Absolutely. It forces us to abandon simple, deterministic pictures.
But on the other hand, it's also the ultimate source of structure and stability. It provides the rigid rules that allow atoms to form, molecules to bond in specific ways, leading to chemistry, the periodic table, everything.
Exactly. It's both the weirdness and the order. And that very order, that precise structure provided by quantization, is what we've learned to harness.
Through engineering those energy levels, spins, band gaps.
Yes. Understanding and manipulating these quantized properties is what gave us lasers, semiconductors, MRI, and potentially future quantum technologies, too.
So ultimately, quantization shows us a universe built not on a smooth, yielding continuum, but on a fundamentally discrete, resilient, and maybe even computational framework.
A structure that's both the bedrock of reality as we know it and holds the keys to its deepest remaining mysteries, especially concerning gravity and the nature of space-time itself.
It really makes you think differently about, well, everything. We hope this deep dive into quantization has given you plenty to chew on, and maybe even sparked some curiosity to explore further. Thanks for joining us.